Thanks for the introduction, and good morning, everyone. I'm Yaxiong from Princeton University, and today I'm going to introduce our work on programming the radio environment with large array of inexpensive antennas. The first author, Zhu Qi, cannot make here today, so I will present the paper. So let's get started. In the past few decades, we have witnessed the huge success of wireless communication. We use like Wi-Fi, Bluetooth, and LTE almost every day. But it's still widely known that wireless communication still face significant challenge, especially in high throughput applications like the VR, AR applications, or in some dense deployment like IoT scenarios. And the fundamental problem of wireless communication is that the wireless channel is noisy and unreliable, so we can always observe errors during the transmission. And to cope with the noisy channel, a lot of solution has been proposed. For example, the first direction is to leverage the channel coding like the spinal code, LDPC code. They will add some redundancy to protect the packet. Another direction is to leverage the diversity, like the link diversity. MRD leverage the link diversity by choosing a better link to transmit the packet if we have multiple senders. And the OFDM leverage the frequency diversity by sending different information over different frequency. And the MIMO technology leverage the path diversity by transmitting different information over different multipath. So if we summarize all the previous works, we can find that all previous works focus on endpoints. They either optimize the sender or receiver. But we ask the question that, wouldn't it be nice if we can change the channel itself? Of course, by changing the channel, it doesn't mean that you should physically change the environment, like you break the wall to let the signal go through. Sorry. Actually, by changing the channel, we mean that we should implement some electronic device in the environment so that we can reconfigure the environment electronically and programmatically. Specifically, we instrument the environment, like the wall with a lot of inexpensive antennas. We call it LAIA. And each LAIA element is actually very simple. It is two antennas connected with a phase shifter. And the endpoints, like the AP, will measure the channel and send the channel measurements to a lightweight server, which will calculate the optimal phase configuration of all the phase shifters. And then the phase configuration will be sent through a control plane to all the LAIA elements. This is our design, but how our design works, how can we reconfigure the wireless channel? Let's look at this example with two paths. So the signal travels along different paths will add it together at the receiver. Due to the difference of the time of arrival, sometimes they will add deconstructively, so the signal strength is minimized. Imagine that if we instrument these paths with a LAIA element, so the signal will be received by the first antenna of the LAIA element, then be phase shift by the phase shifter, and then be received by the receiver. If we shift the phase to the correct amount of shift the signal with correct amount of phase, we can actually, it is equal to delay the signal in the time domain. If the delay is correct, we can make then add it constructively, and the signal strength can be maximized. So our goal is to align all the environmental paths. And the same principle applies if we have multiple elements. So what we need to do is to find the correct phase shifts to each alignment and make them align with the environmental path. And so on and so forth. We do the same thing for all the elements. But to realize this idea into a real system, we face the following challenges. The first two challenges is to measure the LAIA channel and the environment channel. These two channels are very difficult to decompose because they are superposed together at the receiver. And even we know the channel, we still need to calculate the configuration of the elements so that we can align all the channel together. To introduce our channel decomposition algorithm, we will use this example. We call our algorithm two-probe algorithm because we need two channel probes to decompose the channel. In this example, we have the environment path and we have the LAIA path. And in the first channel probe, we will measure the superposed channel here, which is the summation of the LAIA channel and the environmental channel. And in the second probe, we will shift the phase of the LAIA channel by 180 degrees. And then we measure the channel, which is the superposition of the reverse LAIA channel and the environment channel. If we add the LAIA channel, added the channel measured from two probes together, we can observe that the LAIA channel is actually canceled. So we can calculate the environmental channel using this equation. Similarly, if we rotate the channel measured in the second probe first, and then add them together, it's obvious that the environment channel is canceled in this time, and we can calculate the LAIA channel. To summarize the two-probe algorithm, we can see that from two channel probes, we can factor the environment channel and the LAIA element channel. And what happens if we have multiple elements? So the same principle still applies, but we will treat, in this example, we have two elements, but we will treat the first element, the channel of the first element superposed with the environment channel as the combined channel, and we will shift the phase of the second channel, second element, and do the two-probe algorithms so that we can decompose the channel of the second element and the combined channel. After that, we will align them together like this, and then we will do the two-probe algorithm on the first element and decompose the channel. After we decompose the channel of the first and second element, we can easily decompose the environmental channel, and then we can align them together. And note that during this process, the second element channel is actually not perfect. In the second two-probe, the second element channel is not perfectly aligned with the environment channel, but it won't be a huge problem because typically the LAIA element channel is much smaller than the environment channel. So in our previous introduction, we only talk about like, okay, we're going to align the channel, but how are we going to align the channel? It looks like easy that we only need to shift the phase of each channel to align them, but this only works for narrowband channel. The problem becomes complicated in two dimensions. The first of all, the frequency dimension, because of its channel frequency selective fading, the channel is different in terms of their amplitude or phase at different frequencies. And a key property of the phase shifter is that it will shift the phase of all the channel with the same amount of phase. So if we shift the LAIA channel the same amount of phase and add them together with the environmental channel, we can see that some of the channel is perfectly aligned, but some of them are not. The same phenomenon happens to the frequency spatial domain, where the channel is measured. When the channel is measured from two antennas, the channel is different also. And if we align the same phase shifts to all the LAIA element channel and add them together with the environment channel, you can see that they are not, some of them are not perfectly aligned. And this problem is even more complicated if we have both wide bandwidth and multiple antennas, like the MIMO OFDM channel. So we need to consider both frequency dimension and the spatial dimension and align the channel on these two directions. A Strawman solution could be an exhaustive search. In this example, I will show you how can we do the exhaustive search. Suppose we have decomposed the environment channel and the two LAIA element channel. And for each element, we can shift the channel with 8 different phases. If we randomly select 2 phases from each channel and add them together with the environment, we can get 2 combined channels. And we can, according to the theory, we can calculate their channel capacity, and we can compare which one is larger, and we can select the one with higher channel capacity. And we can do the same thing for all the possible phase shifts of the LAIA element, and we can select the best configuration that provides us the highest channel capacity. But you can see that we have 64 possible combinations here. And if we summarize, we can see that the search space is actually n to power L, where the n is the number of phase shifts and L is the number of elements. And in our experiment, we use 36 elements, and each one has 16 phase shifts. So you can see the search space is so large that we cannot do it in real time if we do it using exhaustive search. So our solution is actually an iterative search, where we only take the first element in and search for the best phase rotation that give us the highest channel capacity. And we fix that phase shifts of the first element and search for the second element now, and find the configuration that give us the highest channel capacity. And we have done our first iteration. But this process cannot guarantee the optimal solution, so we will keep rotate by fixing the second element and research the first element and find the configuration that give us a higher capacity. And we do the same thing for the second element. We fix the first and research the second and find the one with higher capacity. We will keep iterate until we cannot increase the channel capacity anymore. So till now, we have introduced our design for actually only one link. Next time, we will talk about the multiple link scenarios, because in a real deployment, we can always see the multiple links share the wireless median with wireless SMA. So what happens if our system only focuses on one link but doesn't care about another link? If the channel capacity of two links without our system is here, and if our system only focuses on one link, it is possible that our system will harm the capacity of another link. Similarly, the same thing could happen for the second link, if we only focus on the link 2. So we hope our solution to fall into this area. And no link is harmed in terms of their throughput capacity, and of course we cannot increasing the channel capacity unlimitedly. So our solution will be bounded in this area. To summarize, our goal is to maximize the total throughput without decreasing the throughput of any individual links. To solve this problem, we can use theta to represent the phase configuration of all the antennas, all the elements, and the channel capacity is actually determined by the phase configuration, like the link 1 and link 2. And we formulate this problem as an optimization problem. Our objective function is to maximize the total throughput, and is subject to that no one will be harmed in terms of their throughput capacity. Next, I will talk about the implementation. We implement the system on Princeton IoT house. And as I mentioned, we have 36 elements, and each element has 16 possible phase shifts. Next, I will talk about our micro benchmark, which is the controllability. By controllability, we mean the definition of controllability is defined here. Since each element can be shifted with a lot of different phase shifts, and we can find these two provides us the highest channel signal strength and the lowest signal strength, and the controllability is actually defined as the difference between the signal strength, difference between the minimal and the maximal signal strength. To compare across links, we also divide the subcarriers into strong, medium, and weak subcarriers according to some threshold. So it's possible that some links don't have weak subcarriers because they are strong, and also some links may not have strong subcarrier because they're weak. And we also measure in the experiment, we measure the channel controllability of different distance. And for each distance, we measure two links. And this one shows the first 2-meter link, and we can see that there is no weak subcarrier for 2-meter links. And we can also observe that if the link is, if the subcarrier is weaker, we got a higher controllability. And the same pattern applies to the second link. And for the first 6-meter link, we observe that no weak subcarrier also. But for the second 6-meter link, we observe both strong, medium, and weak subcarriers. Still, the weaker the subcarrier, the higher the controllability. Similar things for the 8-meter link, we observe no weak, strong subcarriers. And the same thing happens to the second 8-bit link. And still, the great controllability can be observed for weaker subcarriers. And next, I will introduce our SISO channel capacity. In the first experiment, we turn on all the LAIA elements and measure the channel capacity of the environment channel. And then we turn on all the LAIA elements and measure the channel capacity. We can see a huge improvement. And next, we implement 2 transmitters in the environment and turn off all the LAIA elements, so which is actually MRD. So the throughput of MRD is here. And at last, we turn on all the elements, and we also turn on the MRD link diversity mechanisms, so we can see the channel capacity of MRD plus LAIA is here. And to summarize, we can see that the LAIA can provide more than 50% channel capacity improvement over the environmental channel alone, and it can provide more than 25% over MRD. Next, I will introduce our channel capacity improvement over MIMO links. Here is the channel capacity increase. The x-axis is the channel capacity increase over the environmental channel for 2x2 MIMO. So the max, mean, and median improvement is here. And we repeat the experiment for 3x3 MIMO. So the max, mean, and the median improvement is here. And we also do the experiment for 4x4 MIMO. So we can always observe a very huge improvement, but we ask the question that where is the improvement came from? So for a MIMO channel, the improvement can come from 2 aspects: the increase of the SNR or the decreasing of the channel conditioning. So we dig a little bit into this. We plot the channel condition of all the channel, including the LAIA channel and the environment channel. We also plot the SNR of the LAIA channel and environment channel. So if you look at 2x2 MIMO case, we can see a obvious channel condition in decrease by LAIA, and also observe some SNR increase. And if you look at 3x3, we can still observe the channel conditioning decrease, but the SNR improve is much less. And for 4x4 MIMO, the channel conditioning reduction is still huge, but the SNR improvement is negligible. So we can summarize that the majority of the MIMO gain actually comes from the reduction of the channel conditioning. We also do the experiment for multi-link scenarios. In the first experiment, we will do measure the environmental channel capacity, and we do this is the CDF of over 30 locations. And we also design our channel control algorithm to maximize only link 1. And from this result, we can see that if we only focus on one link, another link may be harmed in some locations. And if we only maximize link 2, the link 1 may be harmed. And the LAIA can achieve both the channel capacity of both channel, but without decreasing any of them, decreasing the channel capacity of any of them. And the achieved performance is very close to only maximize one link. So to conclude this the work, we actually take the first step towards programming the radio environment, which is a quantitatively different approach to the conventional strategy of optimizing the endpoints. We also implement a prototype that can reconfigure the radio environment in real time, and we done extensive evaluation to demonstrate that we can achieve a throughput enhancement that complement many other state-of-the-art methods. So that's all for today's talk, and if you had any questions, I'm glad to take that. Thank you.
Questions?
Go ahead.
This is Shannon from Rice University. I have a question. So, given for example, an office environment with rich reflectors, how many elements you need to deploy to get all the phase shifted?
Generally, the more elements you can we can deploy, the higher controllability we can achieve. So that's our envision, because our element is very cheap, just 2 antennas and 1 phase shift. So we hope that more elements can be deployed in the environment. But we still do some experiment. We're using 9 elements only. We have 36, but we only use 9 elements in one experiment. We can still achieve a very large improvement over the environment channel.
Dinesh.
Hi, Dinesh Paradia, UCSD. I have a question. So can you use it for outdoor setting? Like, what do you imagine would be challenge for doing it for outdoor? Because you could imagine that outdoors, this is very much needed in the sense that they have a lot of problems getting signal penetrated indoors, right? Outdoor environments, can you deploy this relay in the outdoor environments to get connectivity, better connectivity? Like, for example, imagine Windows can be retrofitted with your device and you can get better throughput for LT, for example. So what would be the challenge you imagine?
For outdoor environment, I think for outdoor environment, I think it will perform even better, because for outdoor environment, we have clear paths between multiple sender and the receiver. We can get, we can also deploy more elements because it's very cheap. I think it won't be a problem. I think the same principle applies still to the outdoor environment.
So in terms of getting the channel estimation, because you would have to adapt it to particular channels using Wi-Fi, you were using a specific channel to estimate and adapt it.
Yeah.
Can you do those for indoors as well? Oh, sorry, outdoors as well, sorry.
For outdoor?
We can take it offline.
Sure.
One final question. What is the range of the system, generally speaking, right now?
What's the rate?
Range.
Range of the system. We do the channel measurements for 2 meter, 6 meter, and 8 meter links. We didn't increase the channel the link distance further because due to the house factor, the room size of the house.
Okay. Thank you.
No problem. Sorry.
One last question.
So I wonder, how do you compare this with a phase array solution?
Phase array at the endpoints?
Yeah, endpoints or the base station.
Yeah, I think for like phase array in the endpoints, our design and phase array endpoint is not like you need to choose one. I think our system is orthogonal to the phase array in the endpoint, so we can deploy both of them, and they can work together, and we can achieve higher capacity if we have both.
Let's thank the speaker.
Thank you.